Alright, this is a bonus video for section 10.2, and this video is all about Euler's identity. And this is a really cool identity. What Euler actually proved is that e to the I pi power, so if you take an irrational number and raise it to the power of an imaginary number and a product of an imaginary number and another irrational number, and then to that you add 1, you're going to get 0. So ultimately, if we prove that e to the I pi is equal to -1, we have actually proved this. So I'm going to run you through this proof, and it's actually really cool, and it very highly relates to the section that we're doing right here, right now. So the first thing that we do is we find out that e to the I pi, we just use the standard Maclaurin series for what e to the I pi is, and e to the anything is going to be the summation from n equals 0 to infinity of that anything to the nth power over n factorial. So just to be clear, if I was to write this out using the terms, it would be 1 plus I pi plus I pi squared over 2 factorial plus I pi cubed over 3 factorial plus I pi to the 4th over 4 factorial. Now, I'm going to remind you guys that when you raise I to a power, you get that 4-step cycle. So just going up to the 4th power, I'm only going to go through that cycle once. So I'm actually going to go through this multiple times. So it's going to seem a bit ridiculous that I have so many terms up here, but trust me, I need them. Plus I pi to the 6th over 6 factorial plus I pi to the 7th over 7 factorial, etc. I think I'm going to have enough with just that number of terms on there. Now, to remind you again, here when we're doing the I to a power, well, I to the 0 is just 1. I to the first power is just going to be I. Now, when I take I and I square it, I'm going to get a -1. So this now is going to become minus pi squared over 2 factorial. When I take I and raise it to the 3rd power, that becomes -I. So this is going to be minus I times pi cubed over 3 factorial. I to the 4th power is the same thing as 1. So this just becomes plus pi to the 4th over 4 factorial. I to the 5th power is going to be I to the 4th times 1. That's just going to be plus I pi to the 5th over 5 factorial. And we enter that pattern, pi to the 6th, or I to the 6th, rather, is the same thing as I squared. So that'll be minus pi to the 6th over 6 factorial. I to the 7th is the same thing as I cubed, so this would be minus I pi to the 7th over 7 factorial. So we can actually interpret the pattern here where it's positive, positive, negative, negative, positive, positive, negative, negative, and it's alternating between real and imaginary. What actually makes this easier is if you group all the real numbers together over here, so like 1 minus pi squared over 2 factorial plus pi to the 4th over 4 factorial minus pi to the 6th over 6 factorial, and then etc., etc., etc. Then group all the i's together. So I times a quantity, and since I've got times a quantity, I can just write it as pi minus pi cubed over 3 factorial plus pi to the 5th over 5 factorial minus pi to the 7th over 7 factorial. Now, that looks interesting. It's almost like this is alternating in sign and only counting the even exponents. Hey, I know how to write that. negative 1 to the nth, oh, not x, this time it's going to be pi to the 2nth power over 2n factorial plus I. Over here I've got summation, again alternating, so negative 1 to the nth, and it looks like I'm going to be doing pi to the, instead of 2n, it's odds, so it's going to be 2n plus 1 over the odd exponent, 2n plus 1 factorial. And I know this is going to go to infinity, it's going to start at 0. Well, I kind of cheated here. I don't need to write down these steps because I can recognize what this function is right up here. This ends up just being cosine of whatever the crap the input is, pi, plus I, this right here, since I've got all odds and alternating, it's going to be sine of pi. Cosine of pi is negative 1. Sine of pi is 0. And there you have e to the I pi is equal to negative 1. One of my favorite things in math. All right.